Hi, everyone. Welcome to the ENLA seminar. I hope everyone's staying healthy and enjoying the warmer weather right now. So today we're honored to have Madeleine Udell speaking. She's an assistant professor at Cornell University in operation research and information engineering. So she completed a PhD at Stanford in 2015, and then did a postdoc at Caltech before joining us at Cornell. She has very broad interests in low-rank techniques, optimization, machine learning, which goes along with her boundless research energy. I'll put a link in the chat to an excellent piece of work from her on generalized low-rank models, which extends the idea of PCA to handle arbitrary data types like numerical and Boolean data types. She's also the co-owner of JuliaOp and a developer, or the co-founder of convex.jl, which is a package for convex optimization in Julia. Because of her research, she's won an NSF Career Award last year. She's won the Sloan Research Fellowship this year, and she was a finalist in the Microsoft Research Faculty thing. So if you would like to ask a question during the talk, then you can do that by typing in the Zoom chat window, and Daniel will unmute you at an appropriate time. You can also ask a question on the YouTube Q&A, and Bart will take care of those. So thank you for joining us, Madeleine, and we're looking forward to your work on scalable semi-definite program.
Thank you. It's a pleasure to be here today. Please, don't hesitate to ask questions. I'd prefer to get more questions. It's one of the most fun things about Zoom is the ability to get questions from people, everywhere. So that's the most exciting part. So this is a talk about a sequence of papers that I've worked on with some fantastic co-authors on how you can solve semi-definite programs at extremely large scale. My interest in this was motivated by the work that Alex mentioned before on generalized low-rank models. So many of those problems reduced to large-scale semi-definite programs. And one question that I had is whether it's possible to guarantee that you've got the solution or a solution that's sort of provably good as in terms of its objective value to these problems at very large scale. So let me tell you a little bit more about this work. But first I want to call out the co-authors. So all of this is sort of various parts of these work are joint work with a subset of Lijun Ding, who is one of my students at Cornell, who's graduating this year. Alp Yurtsever, who was a student of Volkan Sever, he's now at MIT. Olivier Vercoq, also a student of Volkan at EPFL, and Joel Trop at Caltech. Okay, let's get started. So first, let me tell you a little bit about the motivation. So I told you about the motivation from an applied perspective a little bit. Let me tell you about the motivation from a mathematical perspective. Okay, so our goal was to develop algorithms that provably solve a problem using storage that's controlled by the size of the problem data and the size of the solution. This seems, kind of natural. You could say, if the problem data comes in and I can store it using, say, n registers on my computer, if I can store it maybe using n floating point numbers, and I can store the solution also using n floating point numbers, then how much memory does it take? Right? How much memory do I need in my computer to be able to actually solve this problem provably and optimally? Okay, so I can't answer that question in general. Instead, let's talk about the answer to this question with respect to a particular problem. So this is a semi-definite program. It's a optimization problem with primal decision variable x, which is a positive semi-definite matrix, a square symmetric matrix that has all non-negative eigenvalues. So we're going to minimize the trace of Cx, right? This is just a generic linear function of the matrix x, subject to a linear constraint on x, ax equals b, and a trace constraint. The trace of x is bounded by alpha. Okay, so that's just to make the solution set of the problem bounded. Okay, so there's three items that we might consider problem data here: the cost matrix C, the linear map A, and the right-hand side B. I mean, I guess alpha is too, but it's a little sort of a nuisance variable, and it's just a scalar, so we don't worry too much about it. So we might ask, for this class of semi-definite programs, can we achieve our goals? So let's be a little bit more concrete. Let's say that the problem has a compact specification when the problem data uses order n storage. So think of that as n floating point numbers. Okay. We'll say the problem is a compact solution when you can output the solution using n floating point numbers. Okay, and order n. And this happens whenever the solution has a constant rank, right? The size of a square n by n matrix is, order n squared. But if the solution has rank r star, then you can output a factorization of the solution, right, that uses r star times n numbers, or big O of n if r star is fixed. Okay. So if you were to try to solve this standard form semi-definite program using a first order method, so a first order optimizer, what does it do, right? Well, at first it writes down the decision variable. At every iteration, it computes something like a gradient, which is the same size as the decision variable, and it makes some kind of update on the decision variable using that gradient, maybe an additive update. Okay, and you'll notice that even just to write down the decision variable, this is an order n squared object, right? It's an n by n matrix. Okay, so if you were to try to solve this problem using a first order method, you would find that the working memory that you need is order n squared. Okay, even though we've said the problem data and solution are both order n. So this does not meet our goals. Okay. On the other hand, I'm going to show you several methods in this talk that will use working memory order n in order to solve this problem, okay, provably, optimally, under some pretty weak assumptions. Okay, so let me tell you more about why we might be interested in solving extremely large scale SDP. So here are a couple of examples of large scale semi-definite programs. One is MaxCut. This is a semi-definite relaxation of the problem to find a cut in a graph that cuts a maximum number of edges. So we're going to separate all the nodes in a graph into two groups such that the number of edges connecting those groups is as large as possible. Okay. And this is actually a natural problem that comes up in a lot of social network applications, also energy systems applications. It's a pretty important problem. Another problem that we might be interested in, and one that's close to my heart, is matrix completion. So if we have we've observed some of the entries of a matrix, and we want to fill in the rest of those entries. What's a good way to do that? And we might say, well, let's assume that the matrix is approximately low rank, or maybe has low nuclear norm. Let's use that assumption in order to fill in the matrix. So this matrix completion SDP is sort of finds the completion of the matrix that minimizes the nuclear norm of that completed matrix. So these are both pretty natural problems, but let's think about the scale at which we'd like to solve them. So for matrix completion, let's imagine that we've got a matrix that tells you where the rows are users, okay, and the columns are products. So this is, Amazon. Okay, so we know which users on Amazon have bought which products. So there are easily a billion users on Amazon, easily a billion products. So if you just form the natural SDP, you formed an SDP with a matrix variable that has 10 to the 18 entries in it. Okay, so this is very large. It does not fit on my computer. Okay, on the other hand, 10 to the 9, right? That's totally reasonable, right? A gigabyte of memory for 10 to the 9. There's no problem. I have my computer has 16 gigs of RAM. My server has 100 gigs of RAM. Okay, it's fine. No, my server has a terabyte of RAM. Okay, so I can fit a lot, but I cannot fit 10 to the 18. Think about MaxCut. So let's imagine that I'm talking about the Facebook social network, okay? And so I've got a couple billion people in my social network. Once again, that would result in, if I want to solve MaxCut on that population, that results in an SDP with 10 to the 18 variables, too big. Okay. I might also consider a phase retrieval problem, which I'm not showing here, but I'll show you examples of it later on. So there you've got a biological sample, and you're going to image this biological sample, and you want to recover it's actually a pixelated image of this biological sample from certain kinds of microscopy measurements. Okay, the dimension of that the dimension of your semi-definite variable in that case is going to be the dimension of the number of pixels that you want to recover in your sample. So if you want a pretty clear image of your sample, maybe with 1,000 by 1,000 pixelated grid, then you're talking about an SDP with 10 to the 12 variables, still too big to represent on almost any computer. Okay. So why would you expect a compact specification? Vaguely, I mean, intuitively, you might expect a compact specification because data is expensive and you're not going to collect much more than a constant amount of data per row and per column, right? You don't expect that I'm not sure that I expect that the number of products someone is going to buy is going to scale with the total number of products available on Amazon. Right? The number of friends that you have isn't going to scale with the total number of people on Facebook. It's going to scale with the people that you meet, you know? And you would expect also that if the solution is compact, then a compact specification should suffice, right? If your solution, you know, only has, you know, if it's rank 5, so there are only 5 numbers that you need to represent your solution per person in your data set, you shouldn't need to collect much more than, you know, something that scales with the number 5 pieces of information. Okay, the problem is already, you know, should be well specified. Why should you expect an order and solution? Well, you know, sometimes, you know, a favorite explanation is that the world is actually simple and structured, and there really is a low rank solution out there. There are also mathematical explanations for this. One might be that if your data is generated by a nice latent variable model. So if you have some latent variable model that gives you an explanation of which users buy which products or which people connect to which others on a social network, you can actually prove that the resulting solution, that there exists a matrix that fits this data pretty well that's of log rank, where the rank grows with the log of the sum of the dimensions of that matrix. And this is, that's actually joint work with Alex Townsend, who's one of our co-hosts. And then there's a even more general explanation that gives a less tight bound, which says that for any semi-definite program, if the dimension of that of the linear constraint is d, so if there are d linear observations, scalar linear observations of your matrix, there exists a solution to the problem with rank order square root of d. Okay, so that's not constant rank, but it's pretty low. Okay. Any questions at this point?
No questions so far on Zoom.
Okay. Great. Okay, so what do we mean by optimal storage? What kinds of storage amounts could we possibly hope for? So what we're going to do in order to talk about this is talk about how are we accessing our problem data, right? Because if we wrote down sort of a dense version of, for example, this operator A, that would already exceed our storage bound, okay? So instead, we're going to assume that we've got a black box implementation of these primitives, right? Of something that maps a vector to C times the vector, or that maps a vector to A applied to an outer product of that vector with itself, and something that applies the conjugate of A to a vector Y. The result is a sort of an n by n matrix operator, which we're going to apply to a vector V. So essentially, these are all the ways of combining the problem data with vectors to produce vector output. Okay, so by construction, these operators have input and output, order n or order m. Okay, where n is the dimension of the variable and m is the number of linear constraints. Okay, and oftentimes it is actually sort of fast and easy. It doesn't take a lot of storage to apply these operators. For example, C is often sparse, A is sometimes sparse. It can also be constructed out of simple operators like Fourier transforms. So although a matrix representation would be dense, actually they can be applied quickly. Okay, so you need order n storage as long as the number of observations is the same order as the dimension of your variable, which I'm going to assume throughout this talk. You need at least order n storage to apply the problem data, and order rn storage to output a rank R approximate solution to this problem. Okay. So we're going to say that an algorithm to return a rank R approximate solution has optimal storage if it uses working storage big theta of Rn. Okay, so not more, not less. Okay, which it's the minimum required to really read in the problem data and output the solution. So let me tell you about what was out there before our line of work. Classical methods from the 90s are interior point methods. These work extremely well in the sense that they converge very quickly as a function of the number of iterations. They have quadratic convergence. On the other hand, their storage is quadratic in the dimension of the variable, and the storage required is at least quadratic in the dimension of the variable and in the number of constraints. Okay. Primal-dual first-order methods are well, they still have to write down the problem variable, so that's already order n squared. They do a little bit better on the dimension of the constraint. There have been storage efficient first order methods developed, and these are rather interesting. They add on to their given guess of the solution a rank 1 matrix at every iteration. So if you maintain an explicit sort of memory of what these rank 1 updates are, the storage, like the total memory that you need to remember the sequence of rank 1 updates, grows by order n at every iteration. So if you've run k iterations of this method, the total storage you need is order nk. Okay, and there are a lot of really interesting methods like this. They're actually very beautiful, but they either guarantee a bound on the storage used, or they guarantee global convergence to the optimum. And there are no methods like this that can guarantee both. Okay, so they control storage or guarantee convergence. They don't get both. Okay, there's another line of methods that's actually quite different. So these are essentially, convex approaches. These are all approaches that really rely on the convex structure of the problem. There's another line of work that recasts the problem as a non-convex optimization problem. So here we're going to factor the decision variable x as ff star, ff conjugate, okay? And we're going to plug in ff conjugate every time we saw the original decision variable x, okay? And solve that problem as a nonlinear optimization problem, okay? So we can just think about, in order to understand these problems, I mean, actually there were sort of beautiful methods for solving these that I imagine many people on this in this talk have worked on. But let's just consider the properties of the solution of this problem, okay, and the kinds of solutions that we can hope to get to, right? So using manifold optimization methods, we might be able to hope to get to a second order stationary point. We're not going to be able to detect if we're really at a global optimum or not, right, using sort of local methods. So on the one hand, if the rank that you choose for this factored variable is large enough, then any second order stationary point of this problem is globally optimal, okay? And this is a beautiful and fantastic result, which means that you can solve it locally with Riemannian optimization as long as the rank is large enough and guarantee that you've gotten to the global optimum, okay? But on the other hand, you actually can't do better. So if you try to pick a rank that's smaller than this bound, then you can actually get stuck in a bad local minimum. Okay, this is unfortunate. So this says that the rank that you need grows like square root of m, square root of the number of constraints, which means that the total storage required to solve this problem would grow like order n to the 3/2. Okay, so it doesn't quite meet our desiderata that we set. It's also worth noting that for many of these problems, including matrix completion, this thing is not a smooth manifold, and so we can't actually solve it using Riemannian optimization either. Okay, so this approach doesn't work for the class of problems that we're interested in. So let me tell you about approaches that do work, and I'm going to talk about both of these during my talk today. So the first is an approach based on complementary slackness. It can use any, and this is led by my student Li Deng at Cornell. It can use any dual solver to solve the dual to the original optimization problem I showed you. And then we use the fact that the optimality conditions actually identify the range of the primal solutions from the dual solution. Okay, so then we could recover the primal by solving a smaller SDP that lives on that range that we've identified. Okay, now in order to guarantee that you can recover the primal and recover a point that's sort of provably close to the true primal optimum, we require strict complementarity and that the solution really is exactly low rank. Okay. The other class of approaches that we've worked on is I'll generally call sketchy SVP, and there's a couple of papers that use this approach. That's led by Alpert Sever. And it uses a primal-dual solver to solve the dual problem. So it's very important that the solver have a sort of representation of both the primal and the dual in it. And we use the insight that we can sketch the primal during the iteration. So we don't need to represent the primal exactly the whole way that we go through. We can actually just keep a sketch of the primal instead, which for the purposes in this talk, a sketch is going to be, just a projection, a random projection of the primal variable. And then we can recover the primal variable from that sketch. Okay, this allows us to find a low rank approximation to a high rank solution. So the second class of approaches doesn't allow you to guarantee that you're necessarily close to the true solution, but it does give you bounds on the distance to optimality and the distance to feasibility for the resulting iterate. Okay, and the nice thing is it also works, right? It does something reasonable, even when the solution to the original problem was not low rank. Okay, so it gives you back something that is a low rank approximation to that high rank solution. Okay. Any questions at this point?
No questions so far as I can see.
Also no on YouTube.
Okay. Then I will press on. So let's talk about this complementary slackness approach first. Okay. But actually, first, since this is a numerical linear algebra seminar, let me connect this back. So the fundamental building block, actually, there are two really important building blocks that are based on core ideas in numerical linear algebra that power this work. So I want to really call these out. So the first is our ability to compute an epsilon approximate eigenvector. Okay, because that's the fundamental primitive that's really powering these computations. So for a symmetric matrix, a positive semidefinite symmetric matrix, we're going to say that a unit vector V is an epsilon approximate minimum eigenvector. If the inner product of the M inner product with V is less than or equal to the minimum eigenvalue of M plus epsilon times the spectral norm of M. Okay. So you're within a little bit of the true minimum eigenvector. Okay. How would you find an approximate minimum eigenvector efficiently? Okay, so I think this group will probably, I hope will believe me when I say that actually if you try to use Krylov methods like eigs within ArcPack, this is actually unstable. It's very hard to control the precision using those methods. And the reason is that in these problems, we tend to see the eigenvalues clustering near the minimum eigenvalue. The minimum eigenvalue tends to have very high multiplicity. Actually, the multiplicity converges to be the rank of the solution to your optimization problem, okay, which is usually greater than 1. Okay, so in that setting, methods like eigs tend to go unstable and they don't work. If you try to run these methods using eigs, they fail. Okay, so instead we actually needed to write our own solvers just to compute approximate eigenvectors. One method that works is the shifted power method. And this converges in about 1 over epsilon iterations to an epsilon approximate eigenvector, and it uses order n storage. A second method that works is a randomized Lanczos method. This converges in order epsilon to the -1/2 iterations. So it converges a little bit faster, but it needs a little bit more storage. You can also get around this by just running it twice, and then it uses the same storage as the shifted power method. Okay, it's just a little bit more complicated. Okay, so the shifted power method, it's pretty straightforward. We're just using power iteration to find the maximum eigenvalue and using the fact that the minimum eigenvalue of M is the maximum eigenvalue of the spectral norm of M times I minus M. So you can see actually just in order to perform that flip, right, to change the minimum to a maximum eigenvalue, this is one of the places where we need to know a bound on the spectral norm of our decision matrix, which is why we needed that bound, trace norm bound on the problem in the first place. Okay. Okay, so what does it look like? You pick a random unit vector, scaled appropriately. It doesn't need to be an exact unit vector. You compute the spectral norm of your matrix, or an approximation is fine. An upper bound is fine. And you run power iteration. Okay, so the main thing that you need to know is how many iterations do you need to run this in order to get an eigenvector over the appropriate quality, and I'm going to return to that question towards the end of the talk. The nice thing about this method, we can actually get a bound on how long it takes. So this is the same as bound I said I mentioned before, so I'm going to go over this quickly. But this allows us to get sort of a complete theory that tells us, how good is our convergence as a function of the number of matrix vector products with our with any n by n matrix. Okay, so it really allows us to get sort of tight bounds on the total complexity of the algorithm. Okay, so now onto this complementarity approach. So now that we know how to compute approximate minimum eigenvectors, we can use that as a primitive throughout these optimization methods. Actually, maybe I should ask for questions because we're ending this subsection.
Yeah, no questions so far here.
Okay, then we will continue. Okay, complementarity. Okay, so I'm going to tell you how to solve these problems using the approach of complementarity. So the first thing that we do in this approach is we move from the primal semidefinite program and we take it to dual. So I'm going to write down the dual semidefinite program, which looks like this. Now suddenly the objective is a linear function of a vector in Rm. Okay, and I've moved the semidefiniteness to the constraint. Okay, so now this constraint is that c minus a star y is positive semidefinite. Okay, so for a large enough alpha, in fact, for an alpha that is less than that, I mean, actually for the bound on the trace will suffice. Okay, you can rewrite this constrained problem as a unconstrained problem. Okay, and that looks like this: maximize b star y plus alpha times the minimum eigenvalue of c minus a star y and 0. Okay, so now I've rewritten my constrained semidefinite problem as an unconstrained problem that has this non-smooth term in it. Okay, once I have done this, notice that I've gotten rid of any semidefinite variable in the problem. The only variable is this m-dimensional vector y. Okay, so any first order method for the dual problem, right, uses optimal storage, right? Because the first order method, it keeps track of the variable, right? Which is just an m-dimensional vector. So if I can compute a gradient and follow the instructions of my first order method for how to update my iterate using the gradient, then I can solve this problem using a first order method with optimal storage. Okay. Great. Now it is important that I be able to compute a gradient using optimal storage, right, without ever using order n squared storage. And to do that, I just need to compute the minimal eigenvalue with an iterative method. So it's possible to compute the minimum eigenvalue of c minus a star y using, for example, randomized power iteration without ever forming, any n by n matrix. Okay. And then as far as, what first order method should you use to solve this dual problem, we tried a bunch. Attograd, AttaNGD, and Excelgrad all work quite well. Okay, now to prove, to be able to recover the primal, we're going to need a couple of assumptions. Okay, we call these assumptions regular SDP, though I have to admit that a reviewer recently told us we should call it a simple SDP. So the name may be changed in the future. So let's call it either regularity or simplicity. But here we go. Here's what it is. I'm gonna call it regularity in this talk. Okay. The primal SDP has a unique solution. The dual SDP also has a unique solution. The primal and dual satisfy strong duality, which means the dual objective, the optimal objective value of the dual is the same as the optimal value of the objective of the primal. And if you want storage optimality, you also need strict complementary slackness, which says that the rank of the primal solution is equal to the dimension of the null space of the slack variable c minus a star y. Okay, and that's going to be very important. We're going to use the null space of c minus a star y in order to pick out the range of the solution x. Okay. And in fact, these conditions hold generically, and they even hold generically for problems like matrix completion or MaxCut. So Legion and I have a paper examining, for what kinds of problems do these conditions hold? And the answer is they tend to hold. Okay. Okay, so how do we recover the primal using these assumptions? Okay, let's suppose that we've got a solution to the dual problem, y star. Okay, what we're going to do is we're going to write down the dual slack matrix, C minus A star y. Now we know that strict complementarity holds between the optimal primal and the optimal slack matrix Z. Okay, so that means that actually this rank condition means that the optimal primal variable is supported on the null space of this dual slack variable. Okay, so that means that we should be able to restrict our primal variable onto that null space, right? And still have the same solution to the problem. So that's exactly what we're going to do. So first, we're going to build a basis for that null space. And we're going to represent our primal variable as, right, just as a linear combination of basis vectors on this null space. Okay, so we're going to constrain X to be of the form V star S V star conjugate in the primal SVP, and we're going to search over R by R matrices S. Okay, so now this is great, right? Instead of searching over an N by N matrix, right, we're going to search over R by R matrices where R star is the dimension of this dual slack matrix. Okay, and we can guarantee the solution is preserved because we already knew that the solution X star lives on that null space. Cool. Okay, so here's what an algorithm for solving the problem using this approach would look like. Given the problem data, you're going to compute the solution y star to the dual. You're going to compute a basis v star for the null space of the dual slack matrix. You're going to solve this reduced primal problem. So I've just taken the primal problem and I've pasted in v star sv, vsv star every time that you originally saw the primal variable x. Okay. And this, provably has the same solution, right? As long as you identify right, VSV star with the primal variable x. Okay. So that's all great. In fact, it's even more great. The reduced primal is a really easy problem to solve. In fact, when the problem has a rank 1 solution, you can actually look at this. This is minimize. Right, minimize a scalar function of a scalar variable, okay, subject to some number of constraints, right? But if you've got linear constraints on a scalar variable, it immediately identifies the problem, okay, the solution. Sort of immediate to solve. Okay. But even if it's a 5 by 5, 10 by 10 semidefinite problem, it's really easy to solve using even interior point methods are acceptable at this point. Okay, so what's the storage complexity if we want to be very formal about it? Well, we have to compute y star, and we're suggesting to do that with any kind of first order method, like a subgradient method, and that's going to take order m plus n storage. Okay. Remember, m is the number of linear constraints, and n is the dimension of the problem variable. We're going to compute a basis for the null space, and we can do that using randomized linear algebra using order n r star storage, right? Where r star is the dimension of that null space. And we're going to solve that reduced primal problem. If we want to actually get an optimal storage guarantee, we have to do it using a matrix-free method like SCS is a good one, the split econic solver, and that uses order m plus n plus r star squared storage. Okay, so you add it all up, and it's order m plus n times r star storage, which luckily was meets our definition of optimal storage. Okay, great. In practice, you could also use an interior point method to solve this reduced primal because it's small anyway. Okay, let me draw you a picture of what this looks like. Okay, so here's what I want you to think of. So there's we've got this problem. Our primal variable is constrained to the positive semidefinite cone. So this cone K is going to be the set of matrices X that are positive semi-definite that have all non-negative eigenvalues. We have a linear constraint. So let's say the linear constraint looks like this. This is a set of matrices A that satisfy AX equals to B. Okay, and we are trying to go as far as possible in the direction negative C. So let's say let's say this is the direction. This is the direction C. We're trying to go as far as possible in the negative C direction. We're trying to minimize the inner product with C. Okay. So what's the solution to this problem look like? It's this point right here. This is the solution X star. Well, I guess I'm doing a subscript, so X star. Okay. Now, what does this null space look like? The null space is actually going to be this ray. Okay, it's going to be a face of the semi-definite cone. So what we're going to do is we're reducing the problem to finding a point that minimizes the inner product with negative C, subject to lying on this red line and intersecting the line AX equals B. Okay, so you can see that if I ask for a point that intersects AX equals B and is on this red line, actually the solution is already X star. In fact, I don't even need to remember what the objective was. Which interestingly, it's true generically. Feasibility already identifies the solution uniquely. Okay, so that's the picture. On the other hand, okay, so if you're an optimizer, the first thing that you would say after I've given you the story is this is completely silly because we all know that optimization methods, especially first order methods, do not find the solution, right? What they do is they get close to the solution, okay? And with a first order method, you can expect to get close, but you cannot expect to get very close, okay? You're not gonna get, 1e minus, 15. You're gonna get within maybe 1e minus 3, 1e minus 4, okay, in relative error. Okay, so we're gonna get an approximate solution instead. So let's try the obvious fix and let's try to do all of these steps with the approximate solution to the dual problem instead of with the exact solution. Okay, so the first thing I'm going to do is I'm going to compute my approximate dual solution. Why? By running my subgradient solver for some number of iterations and then stopping. Now I'm going to compute, well, I can't compute an exact null space, right? Because it's not going to have an, it may even be that dual slack matrix is not positive semi-definite, right? There could be some negative eigenvalues, and I don't exactly know which eigenvalues correspond to the null space and which ones, if I see an eigenvalue that's like 1e minus 5, 1e minus 6, like, are those 0 or are those not 0, right? It's a little bit hard to say. So instead, what I'm going to do is I'm going to compute an R-dimensional eigenspace with the R smallest eigen of this dual slack matrix with the R smallest eigenvalues. Okay, and I'm gonna have to think about how to pick R. Okay. Now I'm gonna solve this reduced primal SDP exactly the same way I did before, right? But over this little eigenspace V. Okay, to find a primal solution. So what happens when I try to do this? Everything seems reasonable, but can't solve the problem. It's actually infeasible. Okay, so let's go back to the picture to understand what goes wrong. Okay, because you can see, like, if I'm going to do this, what's going to happen, right? I'm going to perturb my, my basis V, right? So this thing, right? This red line, this is V. And what's going to happen when I have an approximate dual solution is I'm going to have a perturbation to V. And you might think, right, so if that lies, if I draw a perturbation to V like this, right, it looks perfectly fine, right? The place where it intersects this line AX equals B is still close to X star. Okay, the problem is something. The problem is there's no reason why this perturbed V, right, lies in the plane of my iPad and your screen. Okay, so imagine this vector coming out of the plane. It no longer has an intersection, okay, with this linear subspace AX equals B. And that's why I get infeasibility. On the other hand, there's a very natural idea, which is find a point in this subspace V tilde that minimizes the distance to the linear subspace AX equals B. right? And at least it's pretty clear from this picture I'm drawing, right? That if I try to find, imagine now that this dashed line is coming a little bit out of the screen from you, right? But if I find the point where it is closest to this linear subspace, it's not going to be too far away from the solution X star. Okay. And that's precisely the idea that powers our work. Okay, so let's see how that works. Okay. Okay, so this is how we're going to recover the SDP using approximate complementarity and make it robust to these infeasibility issues. Okay, so I'm going to construct my dual approximate solution Y. I'm going to compute a basis for the eigenspace of the slack matrix with the R smallest eigenvalues. To find a primal solution, I'm going to minimize the infeasibility, or I might accept an infeasibility of delta and then minimize the loss instead. Okay. Both of these are reasonable approaches. One I'm going to call min fees, and the other I'm going to call min obj. Okay. And in fact, I can get a really nice recovery guarantees under either of these approaches. Okay. For min fees, I need to actually know what the true rank of my solution is. For min obj, I don't need to know the rank of my solution. An upper bound suffices. Okay, and I get guarantees on the suboptimality of my solution, the infeasibility of my solution, and even the distance to my solution. Okay, and this requires a guarantee on distance to the solution. What really requires regularity. Okay, great. How well does it work in practice? I'm just going to show you this figure that shows you that as of so to produce this figure, actually what we did is we solved the problem, the dual problem, to a very high accuracy, and then we perturbed that dual solution. Okay, and as a function of the size of the perturbation in the dual solution, we took each of those dual solutions and we tried recovering the primal using this procedure from each of the dual solutions, and you can see that if you have a very accurate dual solution, you also have a pretty accurate primal reconstruction. As you go to a less and less accurate dual solution, you get a less and less accurate primal reconstruction. Okay, and this is true for a range of parameters. In particular, it's true whether or not you get the rank exactly right, or you use a rank that's a little bit too large. Okay, which is the red line. Great. Okay. Any questions on recovery via duality?
Yeah, there are indeed a few questions now. The first one was by Alex, so please go ahead, Alex.
So my question was very related to what you just showed, which was, I'm assuming in practice you only approximately solve the dual problem. And then I was worried about the approximate basis for null of S being good enough for col of X. I'm still a little bit nervous about what happens if I pick R to be smaller than the cluster of eigenvalues that you have near the minimum.
Yeah, so for this approach, as you can see, the guarantee only holds if you have if the R that you picked is an upper bound on the true rank of the solution. So this approach is not so robust to choosing very low ranks. Okay. The second approach that uses primal dual solvers and sketching is robust to using lower ranks.
I see. Yeah. Okay, thanks.
Cleve had a couple of questions, so I asked him to unmute. Cleve, do you want to go ahead?
Well, hi. This is totally unfamiliar to me. How much is your last graph partially answered the question? Yes, you do experiments, but how big are these problems? What software are you using? Is it Julia or this was like Julia?
Now you're so the person who ran these experiments is Alp, and I believe that he actually did the experiments in MATLAB.
Oh, these aren't MATLAB graphs.
One thing that we sometimes do is save the save the problem data to a file and then plot them using other software. So the software that's used to make the plots does not have to be the same as the software that's used to generate the figures. I believe that we use MATLAB because I recall we were using CDX to solve some of these problems. Now, of course, I am a partisan of Julia, but Alp is the one who actually wrote this code, so I believe it was in MATLAB.
I can see you're usually using an old Unix command called slogin. Slogin is when a professor has a student log in.
That's right.
Okay, thanks a lot.
I've heard it called the G shell, right? You type in your command and the grad student goes and does it.
Okay, there's another question by Nihil Srivastava, so I will ask him to unmute. Nihil, do you want to go ahead?
Hi. Yeah, my question was that you showed two methods, and one of them doesn't depend on the condition number. So is there a conceptual reason for that? Like min-opt-stp seems to have no dependence on this condition number. And I was just asking, how is it because somehow the conditioning of V star doesn't enter the picture in this method?
That is such a great question. I mean, essentially, I'm not sure that I'm going to have a really good answer for you. I think it's worth talking about offline. But here, you're more sensitive to the specification of the constraint. When the constraint is all you're using to solve the problem, if you also remember the objective, then you're a little bit less sensitive to what's going on with the constraint. Yeah, but I think I would, I'd have to, point out lines to you in the proof to really give you more intuition than that.
Okay, so there are no further questions. Go ahead.
Okay. Okay. So let me, so I'm going to show you the approach based on sketching next. And I'm going to think about the best way to do this. So we've got two different approaches based on sketching, one that solves a different version of the problem and one that solves the original problem. So Sketchy CGM solves a subclass of matrix optimization problems. Sketchy CGL solves the full class of semi-definite programs. So I think what I'm going to do is I'm actually going to fast forward over this method. And instead what I'm going to do is I'm going to tell you sort of what's the primitive that we really need for solving problems using this primal-dual method. So it's once again it's a linear optimization. It's a linear optimization oracle, minimizing a linear function g, which is going to be the gradient of your problem, over a set of matrices with bounded trace. Okay, semi-definite matrices with bounded trace. And the solution to this is actually given by the minimum eigenvector of this gradient g. Okay, so once again, you can solve it using randomized Lanczos method without ever forming the gradient explicitly. Okay. Okay. Sorry, this is going to be confusing for you unless I actually go through what we're doing. Okay, let me show you a picture of one method for solving this related matrix optimization problem, where I'm minimizing a smooth function over the set of matrices with bounded trace that are positive semi-definite. Okay, so this is the Frank-Wolfe method, the also called conditional gradient. And here's what it looks like. I'm going to start at a point W0, so that's my initial iterate. And I'm going to look in the direction of the negative gradient at that point. Okay, I'm going to find the vertex of this polytope. Okay, to the point in this bounded set that maximizes my inner product with the negative gradient. And I'm going to move to a point that's somewhere in the convex hull of the initial iterate and this vertex that I found. Okay, same thing in the next iteration. I'm going to compute the negative gradient. I'm going to look at the point that maximizes the inner product with the negative gradient over this polytope, and I'm going to move in that direction. Okay, in somewhere in the convex hull of the previous iterate and the iterate that I'm going to. Okay, so in order to do this, the main primitive that I need is this linear optimization oracle, right? Which I can compute using this minimum eigenvector. Okay, so I can write down the resulting algorithm for my problem. And the main thing to see when we're talking about storage optimality is how does the where are the n by n objects in this computation? Okay, so you can see that the n by n objects, these are the matrix X and also the matrix H, okay, which is this sort of rank 1 update direction. On the other hand, you can see if you sort of stare at this algorithm from far enough away that every time we're really using X, it has an A in front of it. It has an A in front of it, has an A in front of it, has an A in front of it. Same thing with the H, it's an A in front of it. The only place that we see X without an A in front of it is this linear update, okay, which is changing where which primal variable you're at. But you don't necessarily need to keep track of that. You only need to keep track of A applied to X, okay? So let's take advantage of that. Okay, and we're gonna take advantage of that by moving the iteration to use only this low dimensional dual vector, which is A applied to X, and we're gonna remember only a randomized sketch of X. Okay. Okay. So first, I'm gonna stare at this algorithm again. I'm gonna find all the X's, and I'm gonna see that they all have A's in front of them, and I'm gonna replace all of those with low dimensional versions of them. Okay, so. Z, which is going to be A applied to X, and H, which is going to be A applied to H. Okay, so when I make this replacement, right, this linear update is now on the Z's and the H's instead of the X's and the H's. Okay, when I make this change, the algorithm actually stays exactly the same. Okay, everything about the algorithm stays the same. You know, every minimum eigenvector you compute is the same. The sequence of objective values is the same. The stopping condition is the same. But when we get to the end, we don't have the solution to the problem. Okay, we've solved the problem, but we don't have the solution in our hand. Instead, we just have the objective value and we have this variable Z. Okay, so you might hope you could recover the solution from Z. The answer is you can't. For example, in matrix completion, if you've got a matrix that can be exactly completed, the resulting Z is going to be 0. Okay? You cannot recover the solution, right? The missing values that you wanted to fill in using the fact that this matrix has an exact low rank decomposition. So, we need something else. We solved the problem, but we don't have the solution. Okay. So the second idea comes in at this point, right? We want to recover. We need to keep track of some extra information so that we can recover the solution. And the way we're going to do this is using a randomized sketch of the solution. Okay. So what we're going to do is, and this is work with a subset of the same authors on how you can sketch a positive semidefinite matrix or a rectangular matrix and recover a good approximation to that matrix from this low dimensional sketch. So we're going to see, remember, a series of additive updates to our decision variable X. We want to remember how the matrix acts on some random subspace, and we're going to reconstruct a low rank matrix that acts like the solution X. Okay, both of these are going to have low storage and low arithmetic costs. Okay, here's how the sketch works. We're going to draw and fix the standard normal matrix omega. Okay. The sketch is going to track the range of X and the trace of X, okay? So I want to remember a sketch S, which should be equal to X omega for any iterate X. And I'm also going to remember something that should be equal to the trace of X. I'm going to call it tau. The way that I update S and tau is when I wanted to do, say, a rank 1 update to my decision variable X, I'm going to keep track of what effect that rank 1 update would have on the sketch S and on this trace sketch tau. Okay. So you can see that if I update S and tau in this way at every iteration, then I maintain these properties, even though I'm not maintaining the variable X. Okay. Cost order R times N, if R is the dimension of the sketch, to store and update the sketch. Okay, to recover an approximation from the sketch, I'm using a NIST approximation, and I compute this thing. So you can see I've got an R by R pseudo inverse I have to evaluate, but that's not too bad. Okay, I mean, I'm not saying explicitly evaluate the pseudo inverse, but you guys are numerical in your you guys are all experts in numerical in your algebra, and I hope I don't need to tell you that. Okay. If you want a lower rank approximation than the dimension of the sketch, you can use a lower rank approximation to the pseudo inverse. Okay. And what's interesting is you can actually use this trace estimate to determine the error. The nuclear norm difference between X And the reconstruction that you can form in this way is actually, it's not even a bound. It's exactly equal to tau minus the trace of this rank R reconstruction. That's pretty cool. So you can say not only a priori, what is the error going to be, but a posteriori, what error did you make? Okay. We also have an a priori error bound. So it's nice to know that as you collect a larger and larger sketch dimension, your reconstruction will get better and better. But also that if your true decision variable x really is rank R, then x and its best rank R approximation will coincide, and this right-hand side will be 0. Okay, which means that if you, if the primal variable that your iteration was converging to actually converged to a rank R matrix, you would recover it exactly. Okay. So here's how the resulting algorithm looks. Okay, so we've replaced all the x's with this sort of projection z, which is a times x. And then we're also going to keep track of a sketch of x using that updating method that I showed you before to keep track of tau and s. Okay, but I put these inside these sort of object-oriented data structures. Okay, at the end, I reconstruct the matrix from the sketch, or an eigenvalue decomposition of the solution from that sketch, and I return that. This is the guarantee, but I'm not going to tell you the guarantee. Instead, I'm going to show you a picture of what the guarantee looks like. So let's imagine that this squiggly manifold is the set of rank less than or equal to R matrices. I start my iteration on that manifold, and my primal dual method is implicitly tracking iterates that leave the manifold. Okay, so the rank of these iterates can actually get quite high, and so that's why I'm drawing this dashed line of iterates that's leaving this manifold. Now, I'm not keeping track of those iterates, right? I'm keeping track of a sketch of those iterates, and if the sequence of iterates actually converges back down to the manifold, and the solution, the final sort of iterate that I get using the conditional gradient method, if that's actually a rank R matrix, then I'm going to recover it from the sketch, and I'm going to have the x hat is actually equal to this rank R recovered solution. Okay, but again, optimization methods don't get exact solutions, they get approximate solutions. Okay, so instead the picture looks a little bit more like this. Let's suppose that I start at the initial iterate x0, I converge down to a final iterate xCGM. I'm going to recover a rank R approximation to xCGM, x hat. And my guarantee is that the distance between xCGM and x hat is no greater than about twice the distance between xCGM and its best rank R approximation. Okay, so it's actually, it's a pretty good guarantee. Okay, but it's on. Yes.
Can you try to finish in 1 or 2 minutes?
Yes, I'm going to try to finish in 1 minute. Okay, so this method works pretty well. I'm not going to tell you more about that. Okay, how do we extend this to a method for the original primal semidefinite problem? Okay, we go back to this primal semidefinite problem. All I need is a method that has the same kind of properties, where I'm just doing a linear update to my primal decision variable. And that linear update can be computed using sort of a minimum eigenvector primitive. So this was actually a core piece that took us like several years to figure out, to go from the previous iteration of this work to this one. And the method that we needed was an augmented Lagrangian primal-dual optimization method. Okay, so we took that semidefinite problem, we wrote down its augmented Lagrangian. I'm not going to tell you very much about this, okay? So we wrote down its augmented Lagrangian. We come up with a conditional gradient style method to solve this augmented Lagrangian problem. And so this is a primal dual method that converges to the solution of the, to a primal dual solution of the SDP. Okay, so there's some derivation, but now here's the algorithm, and we're going to do the same thing we did before. We're going to stare at the algorithm. We're going to look at how does X appear in this algorithm. Okay, and if you stare at this algorithm enough, you will see that X, just like in the previous version, is always pre-multiplied by A when X is doing any work in the algorithm, or there's just a linear update. Okay, so we can use exactly the same trick as before. We replace X by its low dimensional sketch, and the linear update, we just update the sketch. Okay. what's nice is you can get a full convergence guarantee, and you know exactly how good do the approximate eigenvectors need to be in order to prove convergence of this method to an epsilon optimal solution for the original SDP. Great. So that gives us a full convergence guarantee, and it tells us that we actually only need order epsilon 1 over epsilon cubed calls to a matrix vector primitive, right? Calls to these sort of primitive ways that we're interacting with our problem data in order to guarantee a solution that's close enough to feasible and close enough to optimal. Okay. So that's pretty cool to have a guarantee that goes sort of all the way through. Great. Okay, sketch the solution, we recover from that solution. You can see that the resulting method, so our method is this blue line. You can see that the amount of storage that it needs as a function of the problem size scales much more slowly than any competing method. And again, as a function of the problem size, the time that it takes to compute a solution also scales a little bit better than competing methods. Okay. It also gives you actually good solutions to problems like MaxCut, even compared to methods that are designed explicitly to solve MaxCut problems. Okay, so I'm sorry for going one minute over. So what have I told you? I've shown you 2 approaches to solve large-scale SDPs using optimal storage. One uses approximate complementarity to solve regular SDPs using optimal storage, and the other uses sketching methods to return approximations to the solution efficiently. Okay, so thanks for your attention, and I'm happy to take more questions at this point.
Daniel?
There are no questions on Zoom at the moment. Maybe I can ask some question, Madeleine.
Yes.
So if you take a really hard MaxCut problem, which comes from the like the construction of that MaxCut is NP-hard, so you take like a 3-set problem, you formulate it as MaxCut, then you apply your SDP. So actually solving an NP-hard problem, or I mean a very difficult problem from the original formulation. Where would you expect problems? Is there some problem in the simplicity of the SDP? So at which point?
I actually don't expect the SDP to get substantially harder to solve. What I expect is that the solution that you get to the MaxCut problem using the randomized rounding procedure isn't great.
Okay, thank you.
Yeah, so which, you know, that randomized rounding procedure that you use to get from the solution to the SDP to the solution to MaxCut is going to be, I mean, it's going to work perfectly if the solution to your SDP is rank 1. If the solution to your SDP is higher rank, it's going to work less well. Okay. So it may be that that SDP actually doesn't have a particularly low rank solution, and that's the reason the rounding procedure doesn't work well. And it would also be a reason that our method, I mean, right, if the solution to the SDP has a higher rank solution, has a higher rank, then our methods aren't going to nail this solution to the problem either. On the other hand, the randomized rounding procedure actually it randomly picks out essentially a rank 1 approximation to the solution to the SDP. So maybe it's not so bad that our method already returns a low rank approximation to the solution of the SDP.
Okay, thank you. In the meantime, there was a question by Nihir Srivastava, so please go ahead, Nihir.
Oh yeah, a really great talk. I was just wondering if there's any hope of improving the dependence on the infeasibility parameter to logarithmic instead of polynomial.
Yeah. It would be awesome if you can do that. I don't have any ideas for how to do that. I would be surprised if you could do it, and yet, someone in the theoretical computer science community might be able to, and there are often results coming out of that community that surprise me. Our focus is really on methods that are our focus is on methods that are stable and practical, right? Where you can actually, implement them efficiently and it works as right methods that sort of make sense from a numerical analysis perspective. And sometimes that limits our creativity. So it's possible, but it's you know, if you have ideas along those lines, I would be very interested.
Okay, thank you. There are no further questions on Zoom. Are there any questions on YouTube, Bob?
No questions on YouTube.
Okay, then I hand back to Alex.
Okay, thank you very much, Madeleine, for a great talk. So the ENLA seminar will now take a break for a little bit. So we started the seminar as an online series that we were thinking would only go during the pandemic, but yet there's been so much interest that we are planning to continue. The exact format is a little unclear at this time. However, after Nihil's seminar talk a few weeks ago, that stirred up so much emotion that there is an offspring from the ENLA seminar. And that's this seminar that's being called The Complexity of Matrix Computations. It's going to be run very similar to the ENLA seminar in the sense that it will be bi-weekly on Wednesdays at a slightly different time. If you would like to, like many people in the audience today would probably be interested in this. And if you would like to sign up, you can send an email with the subject join to this email address here. The idea of this seminar is to try to bridge the gap between numerical linear algebra and theoretical computer science. So the discussion that was just happening between Madeleine and Nihal was interesting in that respect. The first session is on the 12th of May. It's on matrix inversion, and the way it's going to be run is there's going to be some speakers that have 5 minutes only, so it's blitz talk, and then we will have a discussion around that. And there's going to be a discussion prompt each week. And the discussion prompt for the first session is going to be, what does it mean to solve AX equals B for an invertible matrix A? What do we mean by precision, accuracy, conditioning, and complexity in this context? So we're really going to start at the foundational gaps that appear in numerical linear algebra and theoretical computer science and build towards other issues. So if you would like to join us for that, then you're welcome to sign up. Otherwise, thank you again for a great talk, Madeleine, and we can have a good day.
And thanks for great questions.